Right. So this all sounds hunky-dory. We've got an enzyme, it's making DNA, and it seems like we should never have any problems. But of course, you do. Okay, so the question is, how often do you make mistakes and why? Okay? And it turns out that while I told you how accurate the overall DNA replication process is, I sort of fibbed a little bit, because what I was really telling you is how accurate the process of duplicating a genome is. And that has in it the process of repair. Okay? And it turns out the DNA polymerases by themselves, for mostly no fault of their own, as I'll tell you in a moment, only get about half that accuracy. Okay? So a DNA polymerase by itself is about, makes one mistake per 10 to the 5th base pairs synthesized. Okay? So it's pretty good, actually. I mean, we'd all be happy if we could type 100,000 characters and make one mistake. But, you know, if you're thinking about your genome, this is kind of crappy, right? I mean, this means E. coli has, you know, dozens, if not hundreds of mistakes per round of synthesis. And in our case, we don't even want to think about how many mistakes we'd have in the process of duplicating our genome. Okay, so the first thing I want to talk about is why the polymerase makes so many mistakes. I mean, I've sort of told you this is a pretty elaborate enzyme that's taking lots of precautions to do it correctly. And it turns out it's really not its fault. So most of the mistakes are pyrimidine to pyrimidine, or purine to purine mistakes. That is, it puts a G in instead of an A, or it puts a C in instead of a T. And this is due to something called tautomer formation. Okay, and the best way to show this is to illustrate it. I'm going to show you two different types of tautomers, but all four bases can switch between either their keto and enol tautomers or their amino and imino. Okay, so in the case of cytosine, typically it's in its amino position, but under rare circumstances, it can change to this imino position. Okay, and what I want you to note is that when it changes, its hydrogen bonding pattern changes. Okay, so here it's got acceptor, acceptor, donor. But when it changes, it suddenly becomes acceptor, donor, acceptor. Okay? And that's going to change who it's going to base pair with. And the same thing with guanine. This is, again, you can do this with adenine. You can do this with thymidine. If you want, you can do a little exercise with that. But here, going from the keto to the enol, you go from having donor, donor, acceptor to donor, acceptor, acceptor. Okay? So what this does is that when that occurs, you can change the specificity of base pairing. So the normal correct status for a guanine, okay, the status in which it spends most of its time is in its keto state. Okay? And in its keto state, it does what it should do. It interacts with the cytosine using its donor-donor acceptor positioning. Okay? But basically, 1 out of 10 to the 5th amount of time, okay? So rarely, it switches into this other position and its enol position, and it turns out it base pairs really well with thymidine then, okay? And so what the polymerase is doing is what it always does. It's using Braille to figure out if it's in the right place. Yes, I have a Watson and Crick base pair because the conformation of this is identical, it turns out, to if there were an A here. Okay? So it can't tell the difference when it goes into this alternate form, and it quite happily puts a thymidine in there. Unfortunately, once you put a thymidine in there, this guanine doesn't stay an enol. It actually very rapidly switches back to a keto. And at that point, the enzyme says, uh-oh, right? I've got a problem because it moves to that next position down. That just added base pair is incorrect now. And so it's no longer going to be double-stranded. It's going to be frayed at the end. And it's no longer going to make those interactions we talked about in the minor groove correctly. Okay? And what that does is it basically stops the polymerase cold. And maybe the easiest way to think about this is thinking about the positioning of this 3' OH. So you can see it's positioned very nicely right here to interact with this alpha phosphate. But you can imagine if this base pair is wrong, and it's now forced to repel one another, which is more or less what happens when those hydrogen bonds no longer are complementary, that OH is not going to be anywhere near where that alpha phosphate needs to be anymore. Okay? So the good news is once it makes a mistake, the polymerase stops and thinks about it. Okay? So tautomers allow mispairing, and it's temporary. Okay? But mispairing slows subsequent synthesis. Okay? So that is nice because it gives our polymerase a little bit of time to correct itself. And it turns out the way it does this is to use something called a proofreading exonuclease. Okay? And for those of you who would like to think about it this way, it's the backspace key or the delete key on a polymerase.